Thanks, Svetlana. Yes, I will tell you a little bit, continue a little bit with discussing how else, what other mechanisms we have to avoid or at least significantly slow down thermalization. And maybe as a sort of as a motivation, so let's recall where we left off on Monday in terms of MBL. So, and let's just compare side by side the properties of quantum margotic phases and many-body localized phases. So for example, in terms of eigenstate entanglement, excited eigenstate entanglement, on the ergodic side we have volume law, more or less maximum that one can have, while on the MBL side you have area law, so as little entanglement as possible. Now, in terms of conserved quantities, in quantum ergodic system you only have a couple of maybe global conservation laws such as energy or particle number, while in MBL you have really as many as possible very local integrals of motion where, well, they're quasi-local, but they remember the sort of initial information you put into the state. And same goes for spreading of correlations, so there is really a big gap between fast spreading of correlations, linear in time in ergodic systems, and this slow logarithmic in time dephasing on the MBL side. So, and really this begs the question whether you can have something in between, because these two things are really on the opposite ends of the spectrum. So in particular, so can we have, for example, phases where eigenstates have a little bit more entanglement, right? Not area law, but a little bit more, but nevertheless they would be not ergodic and would not thermalize. And so I have to say that this is very much still an open question. And let me just mention a few possibilities, because in the recent years people discussed, I would say, 3-4 mechanisms how this could be possible, some other route to avoiding thermalization. And one interesting phenomenon that I will give you a flavor of is so-called quantum scars. So that's there you can have non-ergodicity, or at least very slow thermalization for particular initial states. Big difference to MBL that here you don't need disorder. Then a completely different route is actually still keeping disorder, strong disorder in your system, but imposing extra symmetries. So it turns out that if you have non-abelian continuous symmetries, such as SU2 in your system, so for example, if you have a random Heisenberg chain, then symmetry prohibits conventional MBL in the sense I described it. So symmetry guarantees that the eigenstates would have more than area law entanglement, at least logarithmic in the system size for eigenstates. And this leads to this very interesting, at least intermediate non-ergodic regime, which has different properties. So this is something I'm not going to talk about, but ask me if you're curious about it. This is also very much an open story. Another mechanism which is perhaps the most generic, but in a way sort of does not lead to as dramatic ergodicity breaking and as MBL or this regime, is prethermalization, and that's something I will tell you more about today. There is also something I did not put on this slide, things that go under the name Hilbert space fracturing, where some relatively peculiar conservation laws are imposed, which make the Hilbert space lead to a lot of different sectors in your among eigenstates of your Hamiltonian, and that also dramatically slows down thermalization. I'm not going to talk about that. So okay, so let me start right away with prethermalization in Floquet systems, and I will start with the periodically driven systems. Right, there is this nice experiment from the physics lab where you take a pendulum and start driving the frequency, and then as you crank up the frequency, at some point it find the new, a new equilibrium state or a pendulum. So let's illustrate the principle. That you can use periodic driving to engineer states that are not possible in static systems. And so from the point of view of theoretical description, right, your system has a Hamiltonian that is varying periodically in time, right? And then instead of thinking about your static Hamiltonian, so you can be thinking, of course, now there is no energy conservation in the general case and no notion of the ground state. And you can think about the Floquet operator, which is just the time evolution operator over one driving period. Right? And this operator, you can say, well, it has some eigenstates. This is a unitary operator, so the eigenstates have unit absolute value, and there are some quasi-energies here associated with an eigenstate. And of course, this quasi-energy is periodic, so it lives on a unit circle like quasi-momentum in a crystal. And one idea that have been pursued, that if you're thinking about, for example, start thinking about band structure of a solid or some tight binding model, you can use driving to engineer topological bands, for example, right? You can use it to control the properties of your band structure. So, for example, now, of course, challenge here is that generally you have no notion of Fermi energy because energy conservation is gone, right? And also, this whole picture, we can have this whole picture of bands, provided somehow that we can rewrite Floquet operator as an exponential of some effective Hamiltonian, right? Which would still be physical and would be reminiscent of, for example, some tight binding model. Now, challenge is that, first of all, challenge is that this Floquet Hamiltonian is not unique, right? You can always shift the eigenvalues by 2 pi, and that would give you a whole big family of this effective Floquet Hamiltonians. And moreover, a priori, even the existence of this physical local Hamiltonian is not guaranteed. So in the non-interacting problem, yes. Right, I agree. In the interacting problem, I think imagine then, because then you want to describe dynamics, right? And you want to have some intuition about what your system is doing. So maybe... Right. So, right, and here often, we would see that our intuition for static Hamiltonians fails. But indeed, I agree that if you have, you can define bands just sort of from the Bloch theorem in an interacting. Right, thanks. Now, so people have pursued this idea very fruitfully experimentally and used, for example, driving to engineer Chern bands and Haldane model with cold atoms. And so, for example, here is an experiment from Manuel's group where they also could measure topological invariant, the Chern number of the band, and see that as a function of driving parameters, it goes from topologically non-trivial to topologically trivial. So this has been a very useful tool, and there have been other ideas which perhaps have not yet received such a clear experimental realization, as also in solids, realizing, for example, topological insulators by driving. Now, still, going to this point, ultimately at least the intuition behind this is that this Floquet engineering is that you're trying to use driving to modify what your system is doing, modify its Hamiltonian, right? So let's try to look at it very naively. So you could say, well, I have the Fouquet operator. I can write it as exponential of the effective Hamiltonian. So formally, I can always write the answer. Yeah.
Just a technical question. Do you need the commutation of the Hamiltonian at all times, or?
No, it doesn't commute. That's the difficulty. Yeah, exactly. Thanks. So, and then I can formally at least write the answer in terms of the eigenstates of the Fouquet problem, right? But I have this quasi-energy, and then I can choose any integer multiple of 2 pi, and add to it. And then the question is, okay, so which of these Hamiltonians looks most physical? Right. So that's maybe one of the first questions you can ask about this problem. And there is one limit in which people have known, at least for system of few particles, simple systems such as one spin or an atom subject to periodic perturbation, which is when your system is driven at high frequency, when the driving frequency is much greater than the energy scale of your Hamiltonian, right? So, and then you can develop an expansion in the inverse powers of omega, so which is the Magnus expansion, and that gives you effective Hamiltonian as a sum of higher order terms is in 1 over omega, which have the following structure. So it is iterative formulas where you encounter more and more commutators of Hamiltonians exactly at different moments of time. Going to Marcel's question. Now, so we are thinking about many-body systems, right? And the challenge with Magnus expansion in many-body systems is that it's only known to converge essentially when this holds, right? So that the maximum energy that you can have in your system is smaller than the driving frequency. So then this is guaranteed to converge. And one simple example of that is Baker-Hausdorff formula, when you're just switching your Hamiltonian periodically between the two values, right? There is this way of rewriting it as a sum of commutators. But so now the question is, what do we do when this breaks down, right? And it always breaks down in a truly many-body system. So, and here, again, there has been two routes that people have explored, right? And, I will say in a moment that this fact that Magnus expansion does not converge is related to heating induced by periodic driving. And so one route which is, more, let's say, radical is that you can eliminate heating altogether by many-body localization. So many-body localization can persist in the presence of driving. And then, structures that we discussed last time would still be present now in a periodically driven system rather than for Hamiltonian. But then there is a route which, really has its origin in the high frequency, in this high frequency expansion, which we refer to as Fouquet prethermalization. So Fouquet because, Fouquet theorem tells you exactly that there would be quasi-energies and all that. So, and let me tell you a little bit about that. So what we're going to see is that if you have driving at high frequency, in the sense now that driving frequency is much greater than the local energy scale, so for example, exchange constant in your spin chain or spin system, then heating would be exponentially slow in the driving frequency. And this allows you to have actually an effective physical Hamiltonian, which governs evolution of your system up to this exponentially long heating time scale. And more generally, we would see that this, simple idea, so it's pretty general, and it also gives rise to approximate conservation laws in really a variety of settings. So that's what I want to convey in the first, well, or maybe it would be the only thing that I would be able to cover, but that's okay. So, and let's start with some intuition. So let us now start with a lattice model. So let's say we have some, general fermionic model, short range, right? So here I'm taking a similar model to what we saw on Monday. So you have hopping, you have nearest neighbor interaction, right? And let's say you're now applying driving, where V is either an operator which is acting even strictly on one side or a sum of local terms. Like if you have, for example, applying a field. Then, so let's start naively in the regime when interactions are weak. So let's say V is much smaller than J. And sorry, I guess notation is not too clear. So this is a driving I'm applying, and V is the interaction. So let's say that V is U, right? Such that we don't get confused. And then thing is that if the frequency of my driving is much greater than U, then in order to absorb a photon, you would need to do a lot of rearrangements of your particles, right? So, and you would need to create number of particle Hall pairs, which goes as, well, omega over J, right? So here actually I want omega to be greater than J and U, right? And then at weak interaction, so this would require involving interaction at this order, right? Because I need to act with interaction operators that many times, and then I would get a rate, heating rate, absorption rate, which is suppressed as U over omega to power n. So it's U over omega to power omega over J, right? So and here is the basic intuition for the slow heating, which actually something very very much related has been observed, back, more than 10 years back by the Zurich group, which is the very slow double-on decay in large U Hubbard model. So that has the same origin. Now, turns out that you can put this on sort of this is very general, and really the only thing you require is locality in this problem, and being on a lattice also. So, and let me even give you a bit of intuition how how locality gives rise to this slow heating, also in the regime where interactions are not weak. So this perturbative picture from the previous slide fails. So let's say, let's consider an example, our favorite Heisenberg spin chain with some disorder, with some random field. And for example, you're periodically applying a term which is ZZ interaction. You're modulating some interaction term, so that's something that you can do in experiments. Then, first very sort of simple way to characterize heating is to look at the linear response heating rate. So that would involve matrix elements of this operator, right, and some delta function, so spectral related to spectral function of your perturbation. And you can, locality implies that this quantity decays exponentially as a function of omega, where, roughly J is a characteristic scale of local interactions, and well, n is number of spins. This is just proportional to the volume of your system, of course. And proving this, so let me show it for the case when I'm driving just at one point, right? So my perturbation is purely local. Then I can do the following simple trick. So in this spectral function, I can insert commutators of perturbation with the Hamiltonian, with an unperturbed Hamiltonian, and because of the delta function, that would generate, this is exact, so it would just generate powers of omega in the denominator. So let me do it k times, right? I have this commutator k times of my local perturbation with the Hamiltonian, and then I have omega to power 2k. And what is the game here? So the game is that using locality, then you can estimate how fast this would grow, this commutator would grow with k, right? Because I can just estimate how many terms I would generate, because my, after one commutator, I'll get bigger and bigger operators. I can count them, right? And roughly that grows linearly, support of that grows linearly, and then this operator can commute with any of the local terms of the Hamiltonian in that volume. So at each step, I get, I grow by 1, and I get a factor of the current size. So that's a factorial. First to second, this one, right?
No, the first line, step 1.
Ah, step 1. Okay, so.
You replace the metric element by a combinator, and you get omega down.
Yes, exactly. So, and then I do it k times.
And where does it come from?
It comes because alpha and beta are eigenstates, right? So I have, for example, VH. Okay. Right. So you see how locality, and this is very much in the spirit, of Lieb-Robinson bounds and some related, more recent results which use them to show some property of a many-body system. And then so you see that this goes as k factorial over omega to 2 power k. So at some point factorial takes over, right? But for a while it is, this allows you to bound this better and better. And by choosing an optimal order of, how many commutator to insert, which is omega over j, then you get your bound. So this is very simple, actually. Now, okay, so this is for a purely local perturbation. You can also extend it to, more interesting case when your driving term is a sum of local terms, like some global field or modulating your Hamiltonian. Then you have to work a little bit harder and use Lieb-Robinson bounds in a smart way, and then you can also derive this bound for the linear response heating rate. Now there is more. So this is, of course, very suggestive. That tells you that you're driving for this very long time. It does not do, it does not hit your system. So you can largely think about it as just renormalizing your Hamiltonian. And indeed, so you can, with more work, so you can extend this and show that actually up to this very long heating time, your dynamics is very well approximated by nearly conserved Hamiltonian, which you can compute from the high frequency expansion. Right, so it tells you more or less that this expansion is asymptotic, and tells you where you should truncate it to get the best, the best Hamiltonian, and how well it approximates your dynamics. So, it approximates your dynamics with an error that is exponentially small in omega, but then of course heating, eventually messes it up. And this is why people call this prethermalization, because up to this heating time, your system maybe reaches a steady state given by the effective Hamiltonian, right? It looks like it has a conservation law, but then eventually it realizes, no, there is slow heating, and then it would heat up to this featureless state where you're mixing over the whole phase space for our, the whole Hilbert space for our spin system. Yeah. Mm-hmm. Let's say, I guess I understand why you're asking, because of the initial quench from your.
Yeah, so there is quench.
There is quench. You can also turn on the drive slowly, kind of adiabatically.
Slowly means your time equals 0 is kind of
spread. Right. But you can, I think you have a window, right? You can turn it on much faster than tau star. Well, depends on what you want, right? If you want to, so for example, if I want to prepare a ground state of the effective Hamiltonian, yes. If imagine I have a gap, right? Or, my gap, let's say, if I don't want to do something crazily difficult, like prepare, some frustrated ground state of a difficult optimization problem, which we don't know how to do anyway, right? But let's say I want to, prepare topological ground state of a bunch of fermions sitting first in a trivial band, and then I want to turn it into a topological band, right? So then, okay, it would be the usual ramp. Of course, I'll have to go through the gap closing effectively, and I would generate some excitations, but that can be, the slower I do it, the more control it would be, right? Now, indeed, this is an interesting question, right? But normally, if I turn it on suddenly, right, there is this quench, and I would, indeed, my system would take some time to relax to a steady state of this Hamiltonian, of this effective Hamiltonian. Make sense? And this is, by the way, this is not so much explored, how to, practically, if you wanted to do to prepare a ground state using driving. So there is a bit on that, but not too much. So that's a very good question. And so just a little numerical illustration how this works in practice. So for example, if I take a very simple model, spin chain again, and then switching the Hamiltonian periodically between the two terms, SZ and SX. So there is no integrability, but then you can see that I can see how well this expansion truncated at order n approximates my true Floquet evolution, and I can just look at the norm of Floquet operator minus this exponential of an effective Floquet effective Hamiltonian, and then you see, so here different curves are for different frequencies, right? And actually frequency goes the opposite way, so this arrow somehow flipped itself. So actually, so this is the highest frequency. You see that up to order 16, 15 or so, this approximation gets better, and then it shoots up. And that's exactly because of heating, right? There is no somehow physically there is no way to avoid heating. Here, yes. So here it's n is 15, but then as I am, as my frequency gets small and comparable to the energy scale of my system, then it becomes, I have truncated earlier somehow, right? So it moves. Huh? Yeah. So here you see, here you see kind of you're in the regime where it already starts to break down, right? Because you see that that error you're getting is already pretty large. So for the smallest frequencies, but then I should have put some curves for even bigger omegas, and you see that it really goes. So any questions about that? So I just wanted to give you the intuition behind this mechanism. Of course, now you can imagine that there are many ways to play with it, and so let me just mention them briefly, just to say, take 5 minutes to talk about scars. So this is actually this idea that really uses just the fact, uses locality plus the fact that you have two very different energy scales in your problem, right? And then this technology allows you to construct an approximate conservation law. So for example, going back to the old Dublin story, right? Dublin decay story, which already had actually this intuition. So you can also derive in a very similar way as I outline. You can derive that the Dublin number of Dublins would be approximately conserved up to an exponentially long time in U over hopping, right? And there are, of course, then various other games you can play. You can go to the rotating frame and then get some new conservation law there if you find that some energy scale is much greater than the other, right? So people found many applications of that. Another idea is that while you are in this regime where you have an effective Hamiltonian, you can have some distinction between different phases despite driving and heating, and that goes under the name prethermal phases of matter. So for example, Dominic Else and Chetan Nayak had a very nice work on prethermal time crystals and things like that. Again, sort of building on these ideas, but also understanding that symmetries can certain symmetries and certain types of driving can, for example, lead to the case when your effective Hamiltonian would have somehow more symmetry than you might suspect. And there has been also nice recent experiments with ultra cold atoms and nuclear spins in particular. An experiment from the Munich group, in a way, looked at a system of bosons where this, these results I described do not a priori apply because bosons have unbounded, locally unbounded Hilbert space, right? But then there is an intuition that it should still hold, and probably it is just a technical hurdle that we cannot prove it, but indeed, so we'll keep trying, and same goes for long-range interactions. So there are also many cases where you want to be driving long-range interacting system, right, where things are a bit harder to analyze because locality is not as prominent. So are there any questions about this part before I take a few minutes? And yeah, okay, so then let's continue, and so let me just give you an idea of this quantum scars. So I'll probably take, I don't know, seven minutes or so. Yeah. And so, and this was a nice, nice discovery, which came as a surprise from experiments with Rydberg atom arrays, which have been so in Antoine Brouvet's group, developed over the years, and then this observation came from the CUA collaboration in Boston. So essentially, these Rydberg atoms are, which Emmanuel mentioned a little bit. So they're optical tweezers, and then you can form arrays, and they looked, it's well controllable. You can put them in the positions you like, and then you use Rydberg interaction and Rydberg blockade to engineer interesting interacting Hamiltonians. And this particular experiment that I'll describe, so they were in the regime of Rydberg blockade, which effectively, you can think about two states of each atom, either ground state or highly excited Rydberg state. And they were just at the right distance that two atoms which are next to each other could not be excited simultaneously, because energy cost associated with that is too large, and that effectively leads to constrained dynamics, right? So it's an interesting type of model that maybe we don't, always think about in condensed matter, right? Where interaction leads to somehow constrained phase space. And they looked at this dynamics of this model, where effectively each atom is subject to a driving field which can flip you up back and forth between the two states, right? Plus you have the constraint which really gives rise to non-trivial dynamics. And what they found is that looking at the initial state where you put an excitation on every other side, so this is maximum number of excitations you can have, they saw that various physical observables actually showed signs, well, they did not relax, obviously, on the observation window they had, right? Instead showing these persistent oscillations. So this is surprising because, these are relatively big systems of, 50 atoms. So it is surprising that your initialized in a high energy initial state, your system finds its way somehow back to the same state, and you have this many body revivals. And moreover, for other initial states, yeah. Relaxation time, you mean eventually? Yes, right. With this blockade, you mean? Sorry? No. This is different. I mean, at least, there might be some connection, but it's not. Yeah. So forget, for a second, forget about the first part. This is a different mechanism. I think that's important. So other initial states actually showed rapid thermalization. So this is, right away you see this is very much unlike MBL because you have no disorder, right? And really dynamics depends on the initial state very strongly. And so this model, right? So this model is kind of, simple and nice looking. I can write it by dressing. So X is a Pauli matrix acting on my spin. I can dress it by two projectors on the two sides, which tell me that if you can flip only if both your neighbors are down. If one of them is up, you are frozen. And this has a this has Hilbert space dimension which grows as Fibonacci numbers due to the constraint. And some interesting, you can think about it as a hopping problem on some interesting graph in the higher dimensional space. And now another indication, that this is not like MBL. If you look at the level statistics, right, and you see that this is probability distribution of the level spacing for different system sizes, and you see that it goes, so probability of finding two levels close to each other goes to 0. So this is flowing to the Wigner-Dyson statistics at larger system sizes, so it's not like MBL where you expect Poisson statistics, right? So here you feel that most of states are ergodic, but there are some special states. Now, same thing for entanglement growth. You see that entanglement growth seems linear for any initial states, including the special states that show revivals. So I call it Z2 state here. But then, it grows really a lot slower than some other initial states which show more or less normal thing that you expect from thermalization. And one way, to identify that something unusual is going on is to look at the entanglement entropy of your eigenstates. And I'm plotting all eigenstates here and the entanglement entropy, right? And you see that most of the states follow this parabola, and this parabola is what you expect from the eigenstate thermalization hypothesis. This is just thermodynamic entropy, more or less. But then there is a special band of states existing throughout the spectrum, which have a much lower entanglement entropy. And which, for some reason, remember how we talked about ETH, right? So this band violates ETH. Yes. Yes, so there is a... I think, yeah, that's an excellent question. I think this is much more fine-tuned than MBL. There is some region of stability where relaxation is maybe slow, right? So here you see that these things are a bit more stable than you would maybe suspect naturally from the golden rule, right? And that maybe has to do with some form of prethermalization that's still not known, right? But in general, I think indeed they're much more fine-tuned. For this model, they're not exact, but there is a perturbation which makes them exact, while the system itself is not integrable, right? But I think at the same time, especially Andrei Bernivig and Nicolas Regnault have been constructing, new families of scar models. So, and I think what they find is that if you take a relatively simple, for example, spin Hamiltonians, then often there is something, like that emerging in the spectrum. Right, there are scars. And so in particular, they had a paper just recently where for Hamiltonians with integer coefficients, so which, if I take XXZ spin chain, right, with rational coefficients, so somehow they have a prescription to look for scars, and often they seem to find them. Yeah. Yes. It is. It has a different origin, indeed. Okay, yeah. That's good. We can. Yeah, right. That's indeed 5 minutes. Okay, so but that's essentially I just wanted to give you a flavor of this, right? That this is something where you have a small subset of states which violate ETH, but importantly, you could say, well, there polynomial number of states in this big Hilbert space, right, which is exponentially large. So why do I care? Well, because they have a strong overlap with physical initial states like this 0,1,0,1 state, and therefore they can show up in the experiment, and you can maybe think of using them in some way. And so this is a little bit reminiscent of quantum scars and billiards, right, where you have a chaotic billiard, but then there are these unstable periodic trajectories, which periodic trajectory, you think, okay, this is periodic revival that we observed in the Rydberg chain, and this is associated with a special band of special set of non-ergodic states which remember the structure.
So just to be clear, for you, whatever are not really scarce because they are not resolved on the limit. I mean, these are wash out in the ergodic limit.
Wash out at some time, you mean? Or yeah. So for us, I mean, we are, you know, we are a lot less strict, right? So something that, let's say, something that revives and survives at sufficiently long time, for example, at the experimental time, right? I think we would call it scarce. And a word of caution, I think in the literature, pretty much anything that does not, you know, does not thermalize is often now called scarce, right? So I don't think there is really a good definition, and people have certainly abused this notion quite a lot, right? On that.
They are happening, but you know, surprisingly little, yes.
And maybe last thing I would mention is that, you know, really, so this looks like scars scars in billiard. So, but one maybe nice connection is using time-dependent variational principle with matrix product states that gives you, you know, you observe this mixed phase spaces and then regular regions is where you're finding scars. So that gives you another approach to looking for scars in your model. And so let me just stop here. So I'm really out of time, so I would rather take questions than. Thanks.